All right, everybody. We're going over chapter 7 tonight. And if you go to the Canvas course, you'll see that the Excel stuff, I have all that a video of me going through, how to do everything that we're doing for chapter 7. So I'm not really going to get into a whole lot about Excel and how that does the computations because you can just go watch that video and then just call me or text me or email me if you have questions, and we can have a Zoom separately or whatever. But that video covers everything that we're going to be talking about in theory today. So today we're just going to go over the theory behind what we're doing. And then when you go back and watch that Excel, it'll make sense to you. So when I'm going through the PowerPoints, if it doesn't make sense what I'm talking about, it really shouldn't. I mean, I know that sounds crazy, but hopefully I'm just trying to expose you to it now. And then when you go watch the Excel video and start doing it yourself, then you'll understand. Okay, you'll understand what's going on at that point. So I've had in the past, I've only had one or two students that they wanted to understand everything before they started doing it. And that's just not how what we do in this class works. You need to get a general understanding, and then when you start playing around with it, you'll have those aha moments, and you say, okay, that's it. That's so just get doing it and it'll make sense to you. Okay. And you can always text or call me. Um, and I'll be available unless I'm on the phone with somebody else or the dean or somebody like that. Okay, so I'm gonna go ahead and share my screen and we'll get going so I don't keep you guys here all night. Okay. And let's say I gotta pick one person. Who's outgoing in here? Hold on, let me see who shows up in my screen. Um oh, let's see. Now can you see the PowerPoints now? Okay. Well, let's see who Kenneth, you're on man. It's you tonight, okay? Because you're the one that's showing up in my window. It just picks like three or four people. So sorry to put you on the spot so much. So this chapter 7, um, I was talking to someone the other day who had just finished one of there's like three classes on what we're talking about, right? Three or four. And each one kind of looks at this data analysis from a different perspective. And I know we have at least three different people teaching this class. Okay. So if if you covered some part of the analysis in another course, and then now you have mine and you're gonna have another one later, understand that there's a lot of different types of analyses that you'll be doing. So if another professor taught you one type of analysis and this seems different than what you learned before, well, it's because it is. I mean, it's probably hopefully a different type of analysis, but with some similarities to what you were doing before. So don't expect it to be exactly the same. But what we're looking at in chapter 7 is just regression analysis. Okay. This looks at relationships between two or more variables. Generally, a variable we're trying to predict, which is our y variable, and at least one, if not multiple, predictor variables. We usually call those x variables. Or there's a lot of different names. There's a lot of synonyms for the x and y variables. But nonetheless, we're using some variables to predict another variable. Generally speaking, we're only predicting one variable, though. When we're doing regression analysis, we can't talk about cause and effect. We're just looking at relationships, okay? Because this isn't a true experiment. An experiment needs a control and a test group, okay? So we don't have random assignment to two different groups. So all we're looking at here is just relationships with things. We're not saying one thing causes another, but we can draw conclusions off of the data that we have. Now, you'll see in the PowerPoints, I just kind of have the important stuff highlighted, and this is the short version. If you were here for the first class or watched, I talked about I have a long version of the PowerPoints for you to look at. And then I have this one where I've kind of boiled it down to what we'll be doing in class. And then even further down from that, if I went through all the slides, it would take forever going over everything. So I'm hitting the important stuff that you really need to know to get through the assignments for the homework. So what we're trying to do with regression is linear regression. So when you think about that, just think line. It's really that simple. We're trying to put a line to the data that we have and use that line to predict stuff going forward. So here it calls the response variable the y variable. That's what we're trying to predict is the y. And the predictor variable, see how those are represented by an x? So remember I said we got y's and x's and different names for y and x's, and this is exactly what we're talking about there. And another letter we have is K. It says K predictor variables. So K is the number of, I guess, X variables, for lack of a better word. The number of variables you're using to predict your Y or whatever it is. It could be you're using marketing expense and a few other things to predict sales. Okay, so sales will be your Y, marketing expense and all the other stuff will be your X variables, and the number of X variables you have is your K. Um, and then we'll talk a lot about randomness or error in our analyses here because we know there's always going to be error. We talk a lot in statistics about everything that's been ever been measured has been measured incorrectly to some one degree or another. So we accept that we're off on what we're predicting, but how far off, we'll talk about that as we move along. So regression treats all predictor variables as numerical. So you can't put words into this. So like male or female. Okay. So if you're trying to use gender as a predictor variable, you're going to have to do what we call dummy coding. So you're going to have to assign one gender the number of one and the other one zero. And that's just dummy coding. So you might make male one, female zero. And then in your Excel column, you'll just have zeros and ones instead of male and female, but the zeros and ones mean male and female. So that's what we mean by dummy coding because we have to get those, I guess, categorical variables, for lack of a better word, that use letters and words and turn them into numbers. So that's dummy coding. And you can do dummy coding with, more than two categories. But for now, we're just going to stick at looking at something like gender, where it's just zeros and ones there. Now, here's your linear regression equation. Okay, it's very similar to um, when you used to graph lines in high school. If they still do that, I don't really know what they do in high schools anymore. But it's the same type of thing. So y is what we're trying to predict, and the b is zero. That's your intercept. Okay, you remember how we used to have the equation y equals mx plus b, right? And b was your intercept in high school. This is the same equation. We just moved it around a little bit. So beta zero is your intercept, and your beta of one, x of one, that's your predictor variable. So this is what a regression equation with one predictor variable would look like. Okay, you got your intercept plus the beta is the coefficient of whatever your predictor variable is, and we'll look at those a little bit later. And the e term, this is the error we were talking about, plus e. Now, a lot of times we don't put the error in the equation as a number, but the point of this is to let you know that the error is there. Whatever you're predicting is off because of things that you're not capturing in the model. Now, you remember I talked about linear regression being a line. So generally speaking, if we see a line that slopes upward like this, we know it's a positive relationship, meaning that as x increases, so does y. And then this is a negative relationship here. One variable goes up, the other one goes down. And when we have the horizontal line, that means there's no relationship there at all. Okay. So just meaning that when you look at this horizontal line, if x changes, y stays the same. You see? So it's not telling us anything. Over here, when x change goes up, y goes down. And over here, when x goes up, y goes up. You see? And that's what we're looking at here. So just know horizontal line just means there's no relationship. And then these are positive and negative. But it all makes sense as we get along. So here's the same model we looked at before, but with multiple variables in it. And this is what we'll be doing pretty much the rest of this chapter at least. So beta y is what you're trying to predict. And this is the equation to predict y. So y equals your intercept. And you'll see all this in regression. This will get a lot simpler in just a minute, okay? So just bear with me. Y, this is your intercept plus your beta of your first variable, whatever that means. I mean, whatever that happens to be, and plus the beta of your second beta times your second variable number, and so forth. And it has beta of k, x of k. All that just means to the last x variable that you have plus your error term. And we won't be putting the error term at the end, going forward. But just you need to know error is always there. Okay, so here, this is linear regression in a nutshell to me. This is how I see it. Okay, so we know there's error. Okay, there's error in everything. This line, this is what our predicted line. So here, these are all observations, like those numbers we have in Excel. You know how we have columns of numbers, right? And y is what we're trying to predict. I'm using the other numbers to predict that. So these are just individual observations. And regression creates a line of best fit for these dots, basically. And here's your line. So what you can do, if an X variable is here, like let's just say this represents 4. If X is 4, then you go up to this line here to see what Y is going to be if X is 4. You see? And let's say X, if this was 5, Y would be 5. So you use that to predict things. Okay, this is your error. Your error is how far the dot is off the line. So if we're trying to predict right here, well, we know this is what our prediction is going to be on this blue line, but we're wrong by the distance between the blue line and the red dot. Okay, because this is the actual, data that we have, and this is our predicted variable. So that is what the error means. And we just know that's there, but this is the line of best fit. And then here's just the equation that's graphed here. So beta of 0 is your intercept, okay? And that's your y-intercept over here. And then this is just where you are for that. Okay, so and then well, you'll understand this in a minute when we get to the regression output that you'll have in Excel. Okay, we're talking about interpreting the regression coefficients. So the beta of 0, which is our intercept, is a predicted value of y when each predictor variable assumes a value of 0. So this is kind of what helps us graph the line or starting point. Okay, and then each beta is the change of the predicted value of the response given a unit increase of whatever our predictor is, holding all other predictor variables constant. And we'll actually write this out here in just a second, and you'll understand what all this means. So let's say that if you have this data here, okay, so we're trying to predict earnings. This is our Y variable. And then we're using cost, grad, debt, and city. Okay, those are 4 predictor variables, okay, that we have, our X variables. And so here is our regression equation. So we're replacing Y with earnings. So we're trying to predict earnings equals beta of 0, which is our intercept. That's just our starting point for calculating a number, plus the beta of 1, which we'll calculate through regression, times cost. So this is whatever cost happens to be that you're trying to predict, plus beta of 2 times grad, plus beta of 3 times debt, and so forth, all the way down. So this is the regression equation. Now, here's what your output is going to look like from Excel. So here you see this one that says intercept here. You remember the first class, I highlighted some things and I said, these are all the numbers you need from the output. So this looks exactly like the stuff I showed you then. So this intercept here, this is your beta of 0. So if you got a sheet of paper, just write it. Trust me, this will help you when you go to write out the equation for the homework. This is your beta of 0. And remember how you have beta 0 plus, beta of 1 times cost. So this is a number for beta of 1 here. So you would just put 0.4349 times cost in the equation. Here's the beta for grad, here's the beta for debt, and here's the beta for city. So, and if you plug all those in, and we're asking you to write the regression equation for this, it would look like this. So here's your intercept, and then here's the beta for cost. It was right next to cost in that graph we showed you. Here's the beta for grad and so forth. And then so if you're trying to predict, like let's go through this, holding all other predictor variables constant, if the average annual cost increases by 1, then on average predictor earnings are expected to increase by 0.4349 because this is a number for cost and that's positive. Okay, so we know that's how much it's predicted. And then here's the same thing for city. So we know if everything else stays constant, 1 unit increase in city will increase earnings by $2,526.79. Okay. So if you went through, let's see, here's how you would plug everything in. If you're trying to predict like a cost of 25,000 and a grad of 60 and what's next? Debt of 80 and a city of 1, that would give you 45,408 as your best guess on what somebody's earnings would be. Okay. And that's fairly simple there. So that's regression, how you would plug that in. Here, the only thing I'm going to say about this is some people believe regression analysis or just any analysis where you're using a p-value to see if something's significant. Some people think you shouldn't do that. You should just come up with a point estimate and a margin of error around that. and we need to get away from this whole confidence testing. Okay, that's really all you need to know. I'm not going to go in detail on that, but I want you to know there's another perspective out there that we're not going to be covering in this class. Okay, and here we'll get to some of this stuff in a minute. Residuals. Okay, when we talk about residuals, this is the error term. Okay, it's the difference between the observed and predicted variable of response. So remember, we had the graph in the regression, we had the blue line, and then we had the dots. So your residuals are just the difference between the blue line and where that dot is. Okay, that's a number value that we're going to look at to see if the data we're using fits the type of data that can be used to do regression. So not all data is, I'm trying to think of the best word, not all data is fit to use regression. Okay, some data you need to use something that's not linear regression. So linear regression is a line, right? But all data doesn't follow a line. Sometimes data will have a parabola shape, like a U or an upside down U, or it might go up and down and up and down. You see what I mean? And if you try to put a line to that data, you're going to be off a lot. So what we do is we test assumptions to see if, hey, is this stuff roughly linear so that we can put a line to the data and that have some meaning. And that's why we look at residuals. And we'll come back to those in a minute, but let's take a break from that and look at R square. Now, Kenneth, do we have anything in the comments? Because I can't see the comments from here.
Nope, nothing.
Nothing. All right. So another thing that we're going to use a lot in regression is R square. And I'll just read you what it says and I'll explain it to you. The coefficient of determination of R square, again, two words for the same thing. I'm going to call it R square every time. Quantifies a sample variation in the response that is explained by the sample regression equation. So that probably means nothing to you. But R square tells you how much the regression equation explains. Okay, so again, we were looking earlier at earnings. So an R square would tell you how much this equation can estimate or explain in someone's earnings. Okay, and so R square, well, let's just look at that for now, but we're going to talk in a minute about adjusted R square. But here's a graphical representation if you look at things that way. So let's say the blue is our regression line. Here's our equation. And then we have an unexplained variance and explained variance. Okay. So basically, the R squared represents the amount of variance that is explained. Okay. And then so if you have an R squared of 0.8, you know, you're explaining 80% of the variance, and there's 20% that you're not explaining, okay, out there. So as I was saying earlier, we're always going to be wrong. We're always going to be off. Everything's going to be measured incorrectly. But R squared gives us an idea of how much we are explaining with our equation. And it gives us, almost more importantly, an idea of how much we're not explaining. So it lets us know how much we can trust what we have and how off we are. Sometimes R squared is not good. So if you're comparing models to each other, R squared might not be the best way to do that because one model might have two predictor variables, another might have 20. Okay, so this violates the idea of what they call parsimony. So you want your models to be as simple as possible. So it's easier to boost your R square by just throwing in a whole lot more predictor variables in there, or X variables. Okay, but what adjusted R squared does is it penalizes you for each additional predictor variable. Okay, so it allows you to compare a model with two predictors to a model with, say, any other number besides two, 1, 4, 10, 20, and it's going to penalize the models that have more predictor variables. And the thinking behind that is it keeps you from just throwing junk variables in there. Okay, so it allows you to compare. So if you're comparing models, you look at adjusted R square. If you're looking at one model standalone to see how much it's explaining, you look at the R square. Okay, so that's the big takeaway. And R square adjusted, the adjusted R square, just know that it penalizes you for having extra variables in there. But extra variables can increase your adjusted R square, but it has to get over the hump of the penalty for having an additional variable. So here, like say if we're looking at three different models. Model one has one variable predicting earnings. Model two has three predicting earnings, and model three has four predicting earnings. So if we look at R square, it's what, model 3 is the winner, right? And then, but when we look at the adjusted R square, see how these are lower every time? Okay, that's because it's penalizing you for each predictor variable that you have. All right. So when we look at model 3, that one still wins out, but we look at adjusted R square when comparing the models there. Okay. And we can see like model 3, for instance, is explaining quite a bit more model 2 and 3 than 1. So these are adding to it. So here we would say the best model is model 3 because adjusted R squared is higher for that one. But we would say, but it's explaining, 42.92% of the variance. All right. Because adjusted R squared is used to compare models, but you would still go to the R squared to talk about how much it's explaining. Does that make sense? It will. Okay. If it doesn't already. Um, we have different tests, and we'll look at the regression output again, but a test of joint significance is regarded as a test of the overall usefulness of regression. So if we want to see, does this entire regression equation, the whole thing, all the variables that we have in there together, is that a significant predictor of earnings? And we'll look at the F test for that. So the p-value of the F test we'll look at for that. And then if you want to look at each individual, um, beta here, you just look at the regression output and the p-value next to that. So we're going to hopefully have a, okay, so here's what the regression output looks like overall for F. So you see how the F test for the whole regression model, um, it has, this is a p-value, well, I say p-value, the significance level of F. Sometimes you'll see it listed as p-value, same thing. It's very small because whenever you see the E in here, that means there's a whole bunch of zeros. So it's like 0.000, 13 zeros and then this number. All right, so we would say that this equation is significant because the p-value, which is the significance of F, is less than 0.05. Okay, just write 0.05 down because that's like the gold standard for what we'll be doing in this class anyway. So we know that the model is significant statistically by looking at that. Okay. Next, here, let me, where's your 28? So I want to go back a few and just show you. Let me just, want to go. Okay. So it's like, somebody remind me to go to 28. Okay. Because I want to go back and explain this with a different, okay. So here's a regression output again. So you can see what I'm saying. So this is what it's going to look like in Excel. So, man, okay, hold on. So this is your F here. So this is the significance. This is your output you'll have in regression of your overall model. So this tells you that the overall model is significant. Okay. But if you're looking at individual betas, like individual predictor variables, look at this p-value here. And if it's less than 0.05, you know it's a significant predictor. But if it's not a significant predictor statistically. So we know that cost, grad, and city are significant, but debt isn't. Okay. So these are for individual predictor X variables. This is for the model as a whole. So this is an F test and this is a T test. So I was, I don't want to get off. T tests aren't always used. When you say T test, it can mean a lot of different things. But when we're talking about T tests in the realm of regression, we're talking about the significance of individual predictor variables. Okay, I had someone come up to me the other day asking me a question about mean test and t-test, and we're not going to be talking about that in chapter 7 or probably in this entire class. But regarding regression, we're looking at t-test as being a test of a individual predictor variable. All right, so now here, remember I talked earlier about some sets of data aren't good for using regression, right? Because regression uses a line to predict outcomes, and it might not be a straight line, the data. Like I was saying, the data could have to be like this, or it could be a parabola shape, or any shape you can imagine. Okay. But we know it's probably not going to be a perfect line, but is it close enough? That's what we're looking for. This is more of an art than a science, the part we're talking about here, even though I know it's math. We're just going to look at pictures and say, hey, is this close enough? Okay. So different ones we're going to look at here. So we use residuals and residual plots to determine if the assumptions of linear regression have been violated. So here's some of the things we're going to be looking at here, like nonlinear patterns, changing variability, and correlated observations, and outliers. So outliers, that's just data that sometimes it's just keyed in wrong, right? Other times it's just like if you're looking at income and somehow you got Elon Musk in there, right? He's going to be an outlier and he's going to throw your data off. So here, this is what the residuals of a set of data, or at least one variable thereof. And we see this one's a little bit higher than the rest, but it's not crazy like way up here, right? So we would say in general, there really aren't any outliers there. Maybe this one, but not really. I mean, it's not way off, right? But this is the closest one we have, but we're saying, hey, that's good enough. There's nothing crazy there. All right. And it's really that simple with looking at residuals on these things. Next, we're going to say, is the model linear? So does this follow a line? Okay. And then here's what we'll look at for the residuals for that. So you see how I said data doesn't always follow a straight line. It can be U-shaped or an inverted U-shape or like a wave type thing. So this data here violates the assumption of linearity because you see how it goes down, then it goes back up. Okay. You see how this one goes down and goes back up? So we would say this violates the assumption of linearity. Okay. So then we would say, okay, this data, you shouldn't use regression with this data. All right. You would need to use some kind of curvilinear squared term in there to do that. But that's outside the scope of what we're doing in chapter 7. For the purpose of this class, all you need to say is that it violates the assumption. Okay. Oh, God, I went too far, didn't I? Okay, the next assumption is there's no exact linear relationship among the predictor variables. Here, what you could do is just run a correlation of your data to see if it is highly correlated. So here in Excel, to do that, you would have data in here, but I'm just going to show you how to do this. Hit data and then go to data analysis. And then if you go to correlation and hit OK, you would just put your data in here. Okay, so you would just select the data, put it in there, hit has labels and hit OK. And it's going to bring you up a correlation matrix. And what you're looking for there is anything over like say 0.7 correlation. Okay, because then you would say that those are highly correlated variables. And that's how you would check that out. And let's see next. Okay, the variance of the error term is the same for all observations. Okay, so here we're just looking at, okay, are all the errors consistent? Okay, or some parts of what we're predicting, are the errors way larger than the errors at other parts? And if so, that violates the assumption of regression. So what we're looking for here is a fan shape. Like a fan, you would hold the fan yourself this way with. So you see how this is really tight right here, then it spreads out over here. Okay. And that's the fan shape. Okay. So we would say like this one violates the assumption because it's tighter here and further away there. And here we're just looking at things. We're not really looking at a number. We're just looking at the output. So if it's not like that very first one we looked at, we would say this violates the assumption um, uh, that we were talking about there. Next is the error term is uncorrelated across observations. Okay, so here we're looking at, is there a correlation between the error terms? Okay, so again, we'll look at the residual plots. I go through how to make these residual plots. It's the easiest thing in the world. You literally check one box in Excel when you're running your regression, and it will give you all these plots. Okay, and it'll give you one for each X variable too. But here, this is what we're looking for in correlated residuals. See how this goes up and down and back up again, kind of like a wave, you know? And that's what you're looking for. So if it looks like this up and down and up, you would say this violates that assumption of uncorrelated residuals. And, for the purpose of this class, just leave it at that. So you know that this might not be good data for using regression with. Okay, the error term is normally distributed. And here, the best way to do that is to run a histogram of that. So again, I'm going to get out of this real quick and just bump into Excel. So let's say that you have all your data right over here, right? And then what you would do, you would just go to insert, and you see this thing right here. Click on that and see where it says histogram. And literally, it's that easy. You select the data, hit histogram, and it'll give you a histogram of your data. So let's look at what histograms look like. Okay, can you guys, let's see, Kenneth, can you see all these things? Okay, so when you're looking at a histogram to see if it's normally distributed, you're looking for the bell-shaped curve. Okay, and in a perfect world, your histogram would look like this, but your data is never going to be perfect. Okay, I mean, it's just never going to happen. So here's a more reasonable looking histogram. See, this isn't perfect, right? It's not perfectly symmetrical like this one is, but it has a peak and it goes down on the sides, and it's generally speaking bell shaped. Okay, so we're not looking for a perfect bell shaped curve here, just an approximation of that. But let's say if it looked something like this, where it had two different humps in it, that would violate it. Okay, because it's bimodal. It looks like it might have two means. If it's skewed way off to one side like this or the other side like that, we would say that's a problem too. Okay, but as long as it's generally speaking shaped like this, that's good enough. That's all we really care about. So anyway, that gets you through what you need for chapter 7. Um, and then I think after watching this and me just exposing you to what we're doing, if you sit down and do the Excel now and then you try to do the homework, I think it'll make a lot more sense to you of what we're doing. But we're just putting a line to data, and we're making that line with that regression equation that we're talking about. Okay. So what questions do you guys have? I knew I threw a lot at you in the last 30 minutes.
Okay, I have a question, but on Canvas, you've uploaded data files. So the one under chapter 7, are we using it for practice question or is for the homework assignment you give us?
Well, the data file has it all in there. It has the practice and the homework data. It's all in that file.
Because I see it's like 1,500 data per you open one. So, and with the chapter 7 assignment, you have, I think, highlighted the ones we are supposed to work on. The ones that have the marked on each box. Is that what we are supposed to work on? We are supposed to work on everything that we see under it.
Oh, well, no, if let me go back to, let me share my screen again so I can show you. All right, so if I understand you correctly, you're asking what homework assignments are you supposed to do? So if you go to the modules tab, and again, yours will look different than mine, but scrolling down to the chapter 7. Here's just example ones worked. If you want to look at those, you don't have to. Well, hold on, I'm on the wrong tab. Okay, module 7. So here, if you click on chapter 7 assignment, these are the problems you have to do: 1, 2, 18, 47, and 48. So those are the ones you have to do for your homework.
Okay. So if that part, assuming question 1 needs us to use a data file, it's going to specify which data file you're supposed to use. Because when you go to the data file is like, no, it kind of is a lot. So,
Well,
that's what
see,
I'm
this
saying.
one,
The one
there's
you
not a
use.
data file for the first question. You
Oh,
just need
okay.
to answer the question. You see, you don't
Okay.
even need a data file for that. And same way with the second one. But you see how when it has file, that's when you know. So like even the third one, you don't need that.
Yeah.
But when you get down to,
The last one.
yeah, I'm just trying. Yeah, see this one, file exercise 7.48. And then, so that's the one you'll need that file. And that's in the data file.
Yeah. So that's what I'm saying that does it specify because when you open the data file, does it specify the number? If you
Yeah,
can
it's in the
open the
tab. The tab will tell you exactly. It'll
oh
have that exact name in it. Exercise underscore 7.48.
okay, that's fine. Okay, thank you.
Mm-hmm.
And
Any
also
good
I have
question?
a question um with the portfolio paper, the draft. Can you
Mm-hmm.
um maybe elaborate or give me a little explanation on the peer and non-peer reviews?
Well,
Like,
peer-reviewed journal articles. So if you pull up an article and like, let's just go to Google Scholar. Like I'm just trying to think. I mean, you can put anything in here like goal setting if you're looking at goal setting. And then when you're looking at different things, you see how this says like the Journal of Sports and Exercise, European Psychologist. That lets you know it's a journal article and it's peer reviewed. But if see this is a book, you wouldn't do that, because that's not peer reviewed. I mean, you can use it. I'm just saying, but I talk about a mix of peer reviewed and non-peer reviewed. If it's in a journal, like the International Journal of Management Business, so that's a journal article. But other things that you find, you might have just some data you pulled up or like something from a news story that you're using. Those wouldn't count as peer reviewed. But anything in a journal is and yeah, but the Wall Street Journal, funny enough, is not a peer-reviewed journal article. That's just a news thing. Okay. Does that answer your question? And this is Google Scholar. I talked about using that.
yeah, it answers my question. Thank you.
Mhm. Yeah. Well, people ask that every time.
I have more questions on the paper.
Hmm.
When it talks about paper one, that we must include, like she just said, the peer reviewed and non-peer reviewed.
Hmm.
Do you have, so on this, we're just focusing on the historical and operational parts of the industry?
Well, let me pull up exactly what I got in here so I don't say something wrong. So, okay, so here's the section descriptions. Okay, yeah. Okay, so you have yeah, so just give some context to your industry. Like what it is, where it came from, where it's going. Um, yeah, describe the industry, and give some history of it. So like if you're doing electric cars, you would go back and find out whoever created the first electric car, and then bring us up to speed from there, where we're going, where we've been. But if you're doing something like you don't have to go back to like caveman days or anything. If you if you're doing something like the utility industry, you don't have to go back to like when people discovered fire. Just a reasonable amount of time back in the past.
And when you say, do you just want us to use journals when we're talking about peer reviewed and non-peer reviewed, or
Well, no,
is there?
peer reviewed would be journal articles, and then non-peer reviewed, that's anything else.
Okay. Okay.
Yeah, and if you look through the sample paper, that'll give you an idea kind of, how to proceed. Some people like a sample. They don't like to just start from scratch. And like I said, feel free to use AI, to do this. But I'm grading the output. Okay, so don't just say AI made it. You should give me 100. I'm grading your output however you came about doing.
Do we have so with this first one, do we have a limited number of pages you're supposed to write or any number goes?
Well, I'll never say any number is good because then somebody will turn in 2 paragraphs and say, say that's enough. Um, but hopefully now this is a 6,000 level class. Like you have some idea of what's reasonable for covering what you're doing. I always like to say, like, if Stephen King wrote this paper, it'd probably be 1,000 pages, right? Because it takes him forever to say anything. But other people can say, as much as Stephen King in 5 pages. So just, keep it what would be reasonable, and then I'll give you feedback. So what if you turn it in and it's not enough, I'll let you know. And if it's too much, I'll probably never say it's too much, but if it's not enough, I'll let you know. And that's the whole point of you sending in your drafts of the paper so I can give you feedback along the way.
Okay.
Have I exhausted you guys?
Sir, for the paper, are we supposed to use only library tools for the article, or we can just pull any articles from the internet?
Well, some of them need to be peer reviewed. So I don't care how you go about finding your data, but some of your references need to be from peer reviewed journal articles, and the others can be from anywhere.
Okay.
I don't see anything in the chat. Yeah, there's not. I don't know if I've ever had one of these without a chat question. Does anybody want to put one in there just to make me feel better? I'm just kidding. Okay, any more questions? I'm not in a hurry at all because if we can, like I was saying the other night, if we could drag this out, my wife will have the kids in bed, and I'll be set. Okay. Well, as you're doing your stuff, feel free to text or call me. If you get hung up on something, I can probably answer it really quick because I've taught this class several times. And so don't get stuck and let it frustrate you and you spend a couple hours on something. So just reach out to me if you have a problem, and I'll get back to you just as soon as I can. All right. Okay. Well, thank you all. I really appreciate it, and I will see you next time.